Welcome to all of you. And now we discuss about practical problem 15 Newton's forward interpolation formula by C programming. And Newton's forward interpolation formula for n plus 1 interpolating points, and this is the difference table. This xi, the first column is xi, second column is yi. Let fx, this fx be an explicitly unknown functions, but the values of fx are known for a set of n plus 1 equally spaced values of x, x1, x0, x1, x2, x3, and so on, xn. And the corresponding values of fx, that is corresponding y0, y1, y2, y3, and so on, yn, are given. And this is the difference, first order difference, delta y0, that is the y1 minus y0, delta y1, that is y2 minus y1, and so on. The second order difference, delta 2 yi, delta 2 y0, that is equal to delta y1 minus delta y0, and delta 3 yi, the third order difference, fourth order difference, and fifth order difference. And this is the px is the Newton's forward interpolating polynomial, which is degree of at most n for n plus 1 interpolating points. And this is the formula: px equals to y0 plus u by factorial 1 delta y0 plus u into u minus 1 by factorial 2 delta 2 y0, and so on, so on. Here u equal to x minus x0 by h, and this is the dimensionless quantity, is called phase. And this value of u is lies between 0 and 1 to minimize the error. And this Newton's forward interpolating polynomial px is unique, but the representation may be different. And these interpolating points x0, x1, x2, xn are equispaced, and the step length h equal to xn minus x0 by n, which is equal this. And this is the programming for Newton's forward interpolation problem 15. Write a C program to compute the value of fx at 0.20 plus r plus 1 divided by 100 by suitable interpolation formula from the following table. Here x equal to this 0.2, 0.35, 0.50, 0.65, 0.80, 0.95, 1.10, 1.25, 1.40, 1.55, and corresponding fx are given by this, where r is the last digit of your serial number. Here note that is the difference x1 minus x0, that is equal to 0.15, and this is the constant step length for all x, the equispaced. So we can use the Newton's interpolation formula, but we use here Newton's forward because this x, for this x, this 0.20 plus r plus 1 by 100, for this x, this lies between this 0.20 and 0.35. So this x is in the starting um, beginning of the table. So we use a Newton's forward interpolation formula. And this is the programming. This is the variable, double variable x, one dimensional array, 20 memories location, 20 spaces, and y 20, and d is the difference, 20 20 two dimensional arrays, and sum x0, the starting value of x, and xx is the value of x for which we find the value of fx, and u is the phase, and this term, and these integer variables are n, m, I, j, and r. And R is the last digit of your C roll number. So first enter the value of R and scan the value of R, and we here write this the value of the x0, x1, x2, x9 up to x9, the all interpreting nodes arguments this, and these the y0, y1, y2, and this the y9, and this last we put here semicolon, and this put here semicolon here. And this xx, the value of x for which interpolation is required. This is the 0.20 plus r plus 1 by 100, 0.0. Here must put divided by 100.0. If you omit this decimal point, then the result may be uh, error. There is some error for not putting this decimal point. Now calculation is the n equal to 10 because there are 10 nodes argument interpreting points here. So n equal to 10, and the number of subintervals is n minus 1. So n equal to n minus 1. This is the n plus 1 arguments there are. So here modify n, this is the n minus 1, actually n plus 1, that is the 9 plus 1 Newton's forward interpolation formula here. This x0, this is the x0 is the starting value of x, so this, and h equal to xn minus x0 by n. Xn minus x0, that is xn means x9 minus x0 by 9, that is the step length, equal step length, equispace step length. And for I equal to 0, I less than equal to n, I plus plus, that is d I0 equal to yi. So by this di0, there is two-dimensional arrays. This for I equal to 0, so d00, and this that gives this y0. So d00 gives the value of y0, and d10, this is the y1, and d50 up to d90 is equal to y9. So di0 actually gives the first values of fx, values of gives the values of fx for this di0. Next, for this j loop, j equal to 1, j less than equal to n, j plus plus, for j equal to 1, we get the first order difference, that is delta y, and this for j equal to 2, we get the second order difference delta 2 y, and so on. And next, innermost loop, this I for I loop, for I equal to 0, I equal to n minus j, and I plus plus. So initially first j equal to 1, so I equal to 0. Then last value of I is this n minus j, that is n, here n equal to 9. So 9 minus 0, so it is 9. So first for j equal to 1, for g equal to 1, n equal to 9 minus 1, that is equal to 8. So I equal to 0 to I equal to 8, so we get this d01 d01 equal to the d10 d1, this j minus 1 0 minus d00. So d01 equal to d10 minus d00, and d01 is the difference, delta difference, this is the y1, and d00 is the y0. So actually the first order difference, this is the delta y0, this gives delta y0, we write here d01, that is the y1 minus y0, and then d d01 d11, and so this y2 minus y1, and so on. So we get first j equal to 1, this is the j equal to 1 here. So j equal to 1, this is the first column, we get j equal to 1, this is the delta. So for j equal to 1, the first order difference, and I equal to 0 to 8. So from this first this column, for this delta difference, first order difference, this delta 0, delta 1, delta 2, and delta 3, delta 4 up to delta 8, because here there are 10 interpolating points here. So again, next j equal to 2. J equal to 2, this is the second order difference, and from this table, difference table, this delta to y, actually the second order difference, delta to y0, delta to y1, delta to y2, delta to y3, up to delta to y7. That is the delta to y0 equal to delta y1 minus delta y0. This difference, this. So when j equal to 2, and this is the second order difference, and this I runs from 0 to 2 minus, this is the 9 minus 2, 9 minus 2, that's 7. So when j equal to 2, I runs from 0 to 7. So for j equal to 2, we get this the second order difference delta to y. And similarly, for j equal to 3, third order difference, and so on. And now print the difference table is this, for I equal to 0, I less than equal to n, I plus plus, that is for j equal to 0, j equal to less than equal to n minus I, j plus plus, and print this the percentage 15.12 LF. This is the long floating. Actually, this is the 15 point. The total number of places is 15, and the decimal places reserved for decimal places is 12 decimal places here. So LF is the long floating, because we first we define this variable double. So we use the floating LF, and this is the floating LF, and this the difference table is this, person black slash t, that is the tab, and dij. And next for j loop, so first I equal to 0, and j equal to 0 to 9 minus 0, that is 8. So first in the by this for loop I equal to 0, we get the first row of this. So this is the y0, delta y0, delta 2 y0, delta 3 y0, delta 4 y0, delta 5 y0, fifth order differences for I equal to 0 to up to 9. Next, j equal to 2, actually second order difference. So I equal to, next I equal to 1, and j runs from 0 to 9 minus 1, that is 8. So this is the I equal to 1. So we get this I equal to 1 for this delta y1, delta 2 y1, delta 3 y1, and delta 4 y1. This is the, and next, printf enter the column number in which the noise level appears, otherwise press 0. And what is the noise level? Here the noise level, actually very important definition, noise level in this Newton's forward interpolation formula. If the step length h is small, the successive differences gradually decreases in significant figures, and owing to propagation of errors, the errors gradually increase in the successive differences. Hence, a stage is often reached at which the computed differences are of same order as their errors, so that these differences are thoroughly unreliable and useless. And this stage is called the noise level. And to avoid this, remember these points. In a difference table, the computation of differences should be stopped just before one gets differences having only one significant figure. And number two, one figure differences and differences further on should not be used in the computation. And number three, a difference table has to be stopped just before the differences become irregular. So this is the noise level, and this is the points to remember when there is noise level. So in this program, if there is noise level, and put the column number here, this, otherwise if there is no noise level, put this 0. So when m equal to 0, that is m equal to n, here n equal to 9, so m equal to 9, else m equal to m minus 2. if you put m equal noise level at the level 5, so value of m is 5 minus 2, that is 3. And this u equal to xx minus x0 divided by h, that is the u is the phase. So this is the phase. Actually this is the xx is the point at which for which the interpolation required for this point, this 0.20 plus r plus 1 divided by 100, and this sum equal to y0, and this is the sum equal to y0. This is the formula. This is the px is equal to sum equal to y0, and then term equal to u, and for j equal to 1, j less than equal to m, j plus plus, sum equal to sum plus term into d0j. So sum present sum equal to previous sum, this is equal to y0 plus term equal to u into d01 d01. So this is the this u d01 actually delta y0 by factorial 1. So this for I j equal to 1, we get y0 plus u into delta y0. Next term, new term equal to the old term, previous term, that is equal to u into u minus j. Here j equal to 1, so u into u minus 1 divided by j plus 1, that is 2 divided by 2. So next term is this. This term is this u into u minus 1 by factorial 2, and this. So this next for j equal to 2, the new sum equal to old sum. Actually old sum is this u plus u by factorial 1 into delta y0 plus term. This term is this u into u minus 1 divided by factorial 2, and d02. D02 actually the delta to y0. So after completing this by this j loop, you get the sum and print this value of the sum, this y floating a long lf, the long floating, this percentage sign 6.4 long f l floating lf, this equal to this xx comma sum, and return 0. First save this program and compile, um, and next compile and run this program. So this is the Newton's forward interpolation formula. Enter the value of r, put here r equal to 0, and so you get this is the interpolating points, and here the interpolating points is 10, and this difference table is this. This first column gives the value of y, that is fx. This is the y0, y1, y2, y3, y4, y5, y6, y7, y8, y9. And the second column gives the delta y0. This is the first order difference, and third column gives the delta 2 y0, second order difference. Third column delta 3 y0, the third order difference. Fourth order difference, fifth order difference, sixth order difference, and so on, so on. And the noise level, enter the column number in which the noise level appears, otherwise press 0. So here this is the irregular difference, this 2200, this is the 2200, and this is the negative sign here, and this minus this. So there is some there are some irregularities. This is the noise level, this the at this column. So put here first, second, third, fourth, fifth, sixth, seventh, eighth. So noise level column number in which noise level appears in the eighth column, 1 2 3 4 5 6 7 8 column, and there are noise level because here 2200, and the next row minus 900, and next row is the 700. So this the there is irregularities in this column, so put here the 8. So value of y at the point 0.21 is this 1.295325135540 is the required answer by the Newton's forward interpolation formula. Thank you for watching this video.